Good afternoon to everyone. So we'll start the event exactly at 3:30. Dr. Balasubramanian, are you there?
Yes, Professor, I'm available.
Hello, sir. How are you?
I'm doing fine.
Thank you for sparing your time, sir.
Thank you for giving me the opportunity.
Pleasure is all ours, sir. So if you want to check your slides once, you can share and check, and then by 3:30 we can start the event.
Okay.
Yeah, it is visible, sir. No problem. Also, try to change some slides as well, so that
Share this entire
yes.
screen.
No, we can see it in the full screen mode. Yeah, all fine, no problem.
So now all of the participants are postgraduate students, right?
Mostly, but there are few participants who are UG also from undergraduate, as well as there are few faculties also joined. Few of the participants are also from industry, some research scholars.
Okay, I'll try to feed something for all.
Yeah, yes.
By the way, if for those who are having good amount of bandwidth, they can switch on the camera and provided if they are comfortable with. Otherwise, it will be like speaking to the computer.
Yeah.
Always, this
Mm.
online meetings, lectures. It feels, normally the physical lecture we will be able to see some audience and
Right.
see where they are finding it tough to understand. Try to spend 1 or 2 more minutes on that and try to explain. But here,
So maybe once your lecture is over, so we will open the discussion thing. So at that time, if any of the participant wants to ask you the question directly, so they can switch on their video and then they can directly interact with you. No problem, sir.
okay.
I think in a majority of the cases, there is always a bandwidth issue. So we prefer that their audios and videos should be on mute, so that there should not be any disturbance to the speaker and also to the other things, so
Fine.
that the event should go. Yeah.
I also feel little comfortable if I'm stopped in between and asked questions.
Yes, absolutely.
Then and there, because
Yes.
in some points, if somebody needs clarity,
Right.
it can be said on right away, and so that they can follow the presentation.
Yeah.
Otherwise, thereon they will switch on, physically switch off their thinking.
Yes.
So let the audience can ask their doubts then and there.
Yes. So since you already raised this point, so if any of the participant has any query in between they want to clarify, so they can directly ask the question in between also. So there is no problem as such. So in totality, we have 90 minutes, 60 minutes non-interrupted session for you. And then once you finish your presentation, then we can have a discussion or clarifications on whatever doubts they have.
Fine. Otherwise, okay.
Yeah. Thank you, sir.
Anybody from IAS Truckee members or somebody?
Yes. There are many.
Okay.
So most of the participants, maybe 30 to 40% are from IAS Truckee student members. So I kindly request Kavya and Vikas just to check their screen and their audio and video, whether it's coming all right or not. Kavya and Vikas?
Good afternoon, sir.
1 minute. Kavya, your video, yeah,
no
yeah, now it's fine. Now it's fine. Your audio is coming okay?
Okay, sir.
Okay. Vikas? Mr. Vikas? Yes, Vikas. Yeah, okay. So I think it's fine, right? Okay. So
Yes, sir.
So just 2 minutes and then we'll begin. So Kavya, be ready. So you have to start the proceedings exactly at 3:30, okay?
Okay,
And
sir.
I also request Mr. Mahesh from the IT team to kindly record the session when I say, okay? Balasubramanian sir, if we have a consent from your side, so once your lecture is over, so we would like to post this video on the IIIT official channel. There is a YouTube official channel is there. So we would like to post there so that people from across the country, they will get benefited.
Consent accorded, Professor.
Thank you. Thank you so much, sir.
By the way, our friend is here,
Who?
Professor Sunita ji.
I need to check. Maybe ma'am is not there, I suppose.
So she might have already seen this presentation, I mean, seen this topic, not the exact presentation, but
maybe.
the topic she might have seen.
Actually, she might went for an official meeting or so, so she may not be able to join. But later on, she will definitely watch your recorded session.
Perhaps she has listened to this when I was doing
Okay.
as a part of my PhD.
Okay.
I gave this seminar in this related areas.
Okay,
Which
sir.
she was there already.
Okay, great. Mr. Mahesh, if you are ready, then you can start recording. So we are starting the proceedings of the event. Mr. Mahesh?
Oh, okay, sir. Already started, sir, recording.
Okay, thank you. Kavya, over to you. You can switch on your video and then you can start. Yes, Kavya, go ahead. Kavya, you are on mute. Yes, Kavya, start.
Okay. Good afternoon, everyone. My name is Kavya Reddy, a postgraduate student at IIIT Hyderabad. I feel honored to extend my warm welcome to all present here. On behalf of the ISTRUCT IIIT Hyderabad Student Chapter, I want to take this opportunity to welcome our guest speaker, faculty, scholars, the research fraternity, and all the students to join the online session on the topic Seismic Damage Gradation for Structural Brick Masonry Buildings. It is my privilege to introduce our guest speaker, Dr. R Balasubramanian, who is working as a principal scientist at CSIR Structural Engineering Research Center, Chennai. He holds a PhD from IIT Madras and has extensive expertise in the field of structural engineering. His research focuses on the seismic behavior and performance assessment of masonry buildings, damage gradation, vibration characteristics of structures, and condition assessment of industrial buildings and structural components. He has also worked extensively on ambient vibration, severity assessment, and evaluation of structural assemblages and equipment. With several national and international publications to his credit, Dr. Balasubramanian has made significant contributions through both research and consultancy projects, advancing knowledge and practicing in the domain of earthquake engineering. We are truly privileged to have him with us today. Before we start, a small announcement for all participants. If you have any questions or clarifications during the session, please type them in the chat box. We will address them in the Q&A session at the end, moderated by Dr. P. Praveen Kumar Venkatrao, Faculty Advisor of the Student Chapter. Now, without any further delay, we will turn the time over to our speaker. Sir, over to you.
Thank you very much, Professor Praveen and Ms. Kavya for giving a nice introduction about me. Dear audience, this particular topic is a specific topic. Unlike many of the top lectures of broad in nature, this addresses a specific issue with respect to damage gradation, especially for low-rise structural brick masonry buildings. And the concept of structural performance-based structural performance characteristics-based damage gradation that we have arrived at, that will be presented to you. The lecture is organized as, we'll be discussing about something about damage gradation in broader sense, and then with respect to structural brick masonry buildings, how to carry out development of capacity curves, and then because that forms the basis of the damage gradation for further studies, that, and then we'll be talking about the methodology adopted to scrutinize the possible cases of damage gradation, and then we'll be discussing on the specific issues and how the damage gradation is evaluated, and then we will come out with the summary and conclusion. So first of all, let us understand damage gradation is important, especially in the case of performance-based design, because in performance-based design we try to have a target performance level, and then we carry out the design to achieve the desired or targeted performance, isn't it? So it is the basis on which the entire performance-based design are built in the modern structural analysis and design arena. In this lecture, we'll be discussing different types of damage gradation, and then to a specific case of structural brick masonry buildings, are they fitting to, or should we go for a better one, or a newer one, which is of novel in its concept. So what is damage gradation? To understand that, first we need to know what is damage state or damage grade. Damage state or damage grade is the degree of damage to an element of a building, or a building, or a typical class of buildings, or buildings within a city under consideration, or due to various natural and man-made hazards. But here we will be restricting ourselves with this seismic damage, and then the type of building that we are considering is a structural brick masonry building with a rigid diaphragm. So we know what is damage state, Now, what is damage gradation or scaling? Now, on the either on the ascending order or descending order, if we place these damage states and form a series, then it becomes the damage gradation. In literature, we would have seen there are different damage scales or damage gradation schema that are available. So broadly, we can see that in some damage gradation, they will be giving only the subjective description. In some damage gradation, there will be objective measures. What I mean is that mild damage, significant damage, heavy damage, collapse. So these are all measures of subjective nature. Some damage grades talk about gradation in subjective terms alone. On the other hand, supposing if we are mentioning 0.5 mm crack width or volume loss or permanent or transient drift, the story drift. All these are objective measures where you have some physical quantity to define a damage state. Similarly, we have something called damage ratio or damage factor. They also give objective measure, but they give in terms of financial, they give in financial terms. Like, cost of repair of the building divided by cost of replacement of the building. That is one way of defining a damage. But what we can say, if damage ratio is very small, that is say 0.1, 0.2 or 10%, that order means one can easily identify that the damage is small. Supposing if the damage ratio is 0.7, 0.8 or so, we can understand that the damage is significant, isn't it? So indirectly, they indicate the severity of damage. Whilst the crack width, volume loss, permanent temporary transient drift ratio or maximum ground acceleration, though that is intensity of the earthquake, it is not a structural term directly, but you can consider it as in a collaborative term. Okay. So they give in structural terms. The other one, they give the other set of damage gradation, they talk in terms of financial terms. So what should be, the interest, which are all the damage gradation that are important for what type of people. Say, for instance, for structural engineers, the gradations that are giving objective measure in structural terms will be of practical relevance. For decision makers at a district level or at a state level or at a local body level, the financial allocation and other factors come into picture. And for those decision makers, those damage ratio, damage factor kind of damage gradations are important, practical relevance. So for structural engineer, we'll be very keen on those damage gradations that give damage states in structural terms is of practical importance. And then and henceforth we'll be discussing on that. Subjective description alone means it is purely notional, and variability in understanding from person to person is inherently built in the subjective description only. Understandably, the expression of damage grades as an objective measure becomes imminent for structural engineers. The other one on the financial terms, that are relevant for the decision makers. Now, what are all the different damage state descriptive objective measures that are used in the literature? If you see, crack width, volume loss ratio, and story drift ratio. Though I have not included this the maximum ground acceleration. Okay, because direct. It's not a direct structural term. It is, as I told you already, it is a corroborative. We can corroborate it with that. So now, amongst these three, one can see that crack width is a localized measure. This is because along one particular weak line, the crack width may be significant, but it may not be distributed across the building, isn't it? Right? So it may not truly reflect the overall damage on the entire building. So that's why we say it doesn't truly represent the damage state properly. That is in overall sense. Okay. Similarly, the second parameter, volume loss. That parameter is though sensitive when the volume losses are significant, that is at the higher damage levels. This volume loss will be insensitive parameters at the lower damage levels. The reason is that until some part of the structural part of the building something fall out, there will not be any volume loss. It doesn't represent at all the progress of the damage. Immediately after the fall of any particular portion, you will start observing the volume, the loss in the volume, and then only it starts, isn't it? So all of a sudden it has to jump to that level, and then it will go on increasing, and then it also will happen in like in discrete fashion, one by one, stage by stage. It will not be progressive. It will be happening. Some part will fall at one instance, and after some instance, the other parts will start falling one by one. So it happens as a discrete event. And so will it be suitable for performance-based damage gradation or for that matter vulnerability analysis? It is not, because it is insensitive in the lower damage levels. The other one is widely used the story drift ratio, because story drift is a good indicator of overall damage, because I can corroborate the damage state with the increase in the story drift, isn't it? And also that This maximum story drift can be easily obtained from the nonlinear dynamic analysis. When we perform nonlinear dynamic analysis, the measure what we'll be getting is either acceleration or displacement. So from that, we'll be in a position to get these values at the end of the analysis in theoretical calculations, isn't it? So that's why the story drift become popular. Up to FEMA 356, they have the they were having some kind of a fixed values like 0.1 percentage for the transient drift and 0.6 percentage for the permanent drift, something like that. They used to define 3 damage levels like immediate occupancy, life safety, and collapse prevention. For these 3 states, they used to give some fixed values of drift ratios. Then in the later version, that is AAC 4113, they dropped drift values because they are not really representing the damage level for different classes of buildings. For each and every building, the capacity and the ductility ratios also were finding, was having a lot, it was having a large scatter depending upon the geometry, loading conditions, and what other factors. Okay, that part we will discuss in detail further. Okay. So they dropped the fixed values, but then they brought in deformation control. That is, with respect to the fixed drift level, reaching the peak, and then how much it goes beyond the factor, as a ductility factor they call. From that, they were defining the damage grades for structural brick masonry buildings. I mean, not only structural brick masonry buildings, for all other building categories also, be it reinforced concrete or steel moment resting frames, everything. They brought this kind of a classification. But what was we observed was that those kind of deformation control damage grades are also not sensitive to the behavior of the structural brick masonry buildings because there's both larger variation in the capacity, that is force, okay, and also in the displacement. So we came out with an alternative damage measure and the gradation that we will be discussing after we have a small introduction into the development of capacity curve. This called it improved story shear modeling, and then I will take you there to the definition of damage grades based on the structural performance characteristics. What is that? So for obtaining capacity curve of buildings, you have different models like stick models, simple limit state models, or equivalent frame models, which is widely used. And we have 2-dimensional or 3-dimensional finite element analysis models, because depending upon the rigorousness of the results and what we are looking at, like one can choose which type of model that we can adopt. For instance, for analyzing buildings of historical importance, to identify crack propagation and all that requires 2D finite element analysis model. for other cases where we are trying to assess the overall seismic performance or to carry out performance-based design, that is not required. What you require is a simple model that is sufficient enough to carry out either pushover analysis or incremental dynamic analysis to get the desired outcome, isn't it? So in that sense, the stick models have become obsolete because of their own inherent design. But widely, this equivalent frame model and the story shear models are there. The equivalent frame model, basically what it considers is the vertical portion of masonry are considered as columns, equivalent to columns, okay, and the spandrels or sill portion all are considered as equivalent to beams. So the vertical portion of masonry is approximated as a column, and spandrel or sill portion are considered as beams, and they carry out equivalent frame analysis like a RC or any other building. The other type of model is called story shear model, in which we discretize the plate, a wall, into a set of piers, and then each and every pier will be construed as a deep beam. Difference between equivalent frame model and this is that in equivalent frame model, the horizontal spandrel, they'll be considered as a horizontal element. But if you see, the bed joints will be along the axis of the beams, isn't it? Whereas in the case of vertical portion of masonry, which is equivalent to the column that we are approximating, right? There, the bed joint will be perpendicular to the axis. But in the equivalent frame model, this difference is not addressed. Whereas here, all these are approximated as anybody? What is that? Okay. All these are approximated as non-linear springs, that is, deep beams in vertical directions. Okay. So in that, what the conventional story shear modeling is like, on the top left image, we have 4 components. In a case of a single wall with a single opening, the entire spandrel and the entire sill portion, entire spandrel and the entire sill portion will be considered as one element, and the pier portions are, which are separated apart, they will be considered as separate springs or separate deep. So the load transfer will happen from top spandrel and then distributed to the piers and then to the sill and then to the next story or next floor or the basement. So what we understood is that, and also in each and every component pier, they will be considered as cantilever, approximated as cantilever deep beam or fixed deep beam. In that we brought, in this schema, we have brought in a refinement like what is shown in the bottom figure, where the sill portion as well as the spandrel portion are approximated as constituent piers of multiple constituent piers that are resisting force in parallel action, side by side. Earlier, one element is there in the sill and also in the spandrel. But in this, depending upon the continuity at the top and bottom, because you see, for the element 1, there is continuity above. For element 2, there is discontinuity. And for element 3, there is continuity above. So now we have this set of constituent pairs, component pairs that are resisting force in parallel action, unlike the conventional simplified discretization schema. And also, I told you earlier, the stiffness of the deep beam used to be considered either as a cantilever beam or a fixed beam. But if you see in reality, when there is a continuity at the top, you have some continuity. You have some kind of a rotational resistance. And when there is a diaphragm, you have a full restraint. And in the middle heights where you have continuity, you have partial restraint, partial moment restraint. And so instead of having either two conditions, that is fixed or fixed free condition, we brought in this partial fixity concept, and categorized these elements into 4 types. That is, type 1, which is having continuity on both sides, that is top as well as at the bottom, and type 2, which is discontinuous, which is restrained at the bottom and it has continuity above. Similarly, type 3 is the case where it is restrained on the top and the continuity is in the bottom. And type 4 is that on one side it is fixed, the other side there is a discontinuity. So for these cases, we have obtained the stiffness coefficients and we have used in our improved story shear modeling. Using this improved story modeling, we developed the capacity curve of individual buildings, each and every building. So for that, what we have used is, see this figure. There are 4 parameters. This capacity curve, okay, it has 4 parameters. That is the capacity, stiffness, elastic displacement, and collapse displacement, ultimate displacement. So what, using the previously discussed improved story shear modeling, we can get the initial stiffness. Using the expressions available in literature for different modes of failure, like we have this diagonal shear failure, sliding shear failure, rocking or toe crushing failure. For all these cases, we have expressions for the capacity, determining the capacity. So that we can use here. But the point here is, in spandrel or in the sill, we have continuity physically in the horizontal direction also. So that rocking kind of a behavior will not be there. So in those components that are part of spandrel or sill, except toe crushing or rocking mode, the other 2 modes like diagonal tension failure or sliding shear failure have to be considered. Only in the pier portion where there is no continuity in the horizontal direction, because they are standalone piers, then and they separated at different locations, isn't it? So for those conditions, the probable chance of happening of this rocking mode is there, and so that limit also has to be considered. So with this, what we can get is, for each and every component here, we have this capacity values as well as the stiffness values. From these two, look at this figure carefully. From these two, one can get the displacement, yield point displacement or equivalent yield point displacement, isn't it? That is V by K. Okay. And then for the case of diagonal tension failure through bricks alone, which is a tension failure criteria, which is brittle in nature, that is, the structural integrity will be lost once it happens. That is, it attains the peak and within a short while, the structure will crumble. Whereas in the case of the sliding shear failure or rocking failure, though the separation may happen, still they will stand. Still, they will not fall easily until the toe crushing happens and fall out. The structural integrity will not be lost. That is, despite reaching the ultimate point, still you can have larger deformation. You can permit larger displacement before it actually fails, which is equivalent to the plastic kind of behavior, isn't it? So that is for rocking and sliding shear mode of failure. We can have a larger ductility, and for diagonal tension mode of failure, once this crack happens, once the extent crack happens, what will happen? That they get separated and they fall out. So that's why we will have a lesser displacement, lesser ductility limit for diagonal tension, and for rocking and sliding, we can have a little larger ductility limit. So knowing V and K, we will get the yield point displacement, and then multiplied by the ductility ratio, we can get the ultimate displacement. So with this, we can get the capacity curve of each and every component here in that figure I showed in the previous figure. For each and every one of these component pairs, 1 and 2, 1, 2, 3, 4, 5, for each and every one, we can get the capacity curves, right? And then what we can do is, we can get the capacity curve of the building through an assembly procedure, which I will explain. Is it visible?
Yes, sir. Yes, sir. It is visible.
Okay, now I'll just show you an example problem to have an understanding of this in improved story shear modeling. Okay, so in this building, there are two principal directions along X and Y. Along X, we have 3 walls running in X direction. We have 3 walls running in Y direction. So we'll talk about how to get the capacity curve of the building along these two principal directions. Now this is the roof part, and you all know how the load from the roof can be distributed onto the walls. Okay. So using this, we get the load distribution on one particular wall. So this is the wall 1, 2, and 3. That is wall 1, wall 2, and wall 3. Okay. So from the top portion, it is showing the load distribution as a UDL, uniformly varying, or a constant, or a uniformly distributed, isn't it? So in this case, we are having some 13 component pairs. For all these 13 component pairs, we can get the capacity curve, like one for each and every one. So in this, we have 3 levels. That is, in the sill portion, there are 5 constituent pairs, and the pier portion, there are 3 constituent pairs, and then in the spandrel, there are 5 constituent pairs. Okay, so we'll talk about this wall alone, and then we'll proceed. So now look at this. This is a component pair 1 capacity curve. Similarly, this is component pair 6 capacity curve because they are identical. And they have shown. Yeah. So I told you in that wall there were 5 component pairs in the subsystem 1, that is sill. These are the capacity curves. The small lines here, no? They are the capacity curves of the individual component pairs. Understand? We have this capacity force. We have this initial stiffness from the intercept point is x-intercept point is the displacement delta y, yield point displacement multiplied by ductility factor, you will get delta u. So we have bilinear capacity curve. Can obtain this for all the components. In the subsystem 1 to 5, there are 5, and so they are represented here. So now this subsystem resists force in parallel action, because it is like we are having some 5 springs and they are resisting parallelly the force. So what will happen? The force gets added up. The resistance of 1 plus the resistance of 2 plus resistance of 3 plus resistance of 4 plus resistance of 5 will be the resistance of the composite system 1 to 5, isn't it? From there, you can get the resistance at different levels for each and every point of displacement. Got it? And then, so this point happens. This green point, my mouse pointer is seen there. Look at the green line where the nonlinearity starts first on the left side. So that is indicating the first point of deflection in the capacity curve. Now, first point of nonlinearity. So from there, the nonlinearity starts. So if you are algebraically add these force values, we will get the envelope capacity curve of the subsystem, which is shown in that orange color with the circular marker. Okay. Similarly, in the middle portion, there were 3 components here, 6, 7, and 8. They are also parallel springs. They also resist force in parallel action, and they are separated apart. So in this case, diagonal tension, sliding shear, as well as rocking move, they have to be considered, and then get the capacity curves of these component pairs 6, 7, and 8. Okay, so that is shown in the figure 6, 7, and 8. As these are also resisting force in parallel action, we can algebraically add the forces resistance levels at each and every displacement level, isn't it? To get this composite capacity curve of the subsystem, which is shown in that purple color or violet color with X marker. Okay, because force is resisting in parallel action, resisted in parallel action, and so you are adding up the forces. Similarly, in the top portion, there were 5 component pairs. Okay, they were resisting force in parallel action, and their composite capacity curve is also shown in that orange color with circular mark. Similar, just by adding the resistance levels, we'll get the overall capacity curve. So now we have capacity curve of 1 to 5, capacity curve of 6 to 8, and capacity curve of 9 to 13. So this is here 1 to 5, 6 to 8, and 9 to 13. Now these subsystems are resisting force in series or resisting displacements in parallel. Subsystem 1, this is cell portion. Above that we have subsystem 2, that is pier portion, and then subsystem 3, which is the span travel. So this is in series action, resisting force in series action. On other hand, what we can say, resisting displacement in parallel action. So what we'll have to do, we'll have to add these displacements for each and every level of displacement, each and every level of force. What will be the overall displacement that we can obtain by adding the displacements of the component pairs? Something like this, from left to right. Add the displacement values from the green one. This violet color one is separated farther apart, right? This is after adding the displacement corresponding to that blue and brown one. Okay, up to the attainment of P, the displacements have to be added. Beyond the attainment of P, that is, this plastic hinge formation happens, right? So what happened in a chain, if you consider plastic hinge forms, so beyond that, what will happen? Only that particular spring alone will undergo displacement, whilst the remaining springs will be continuing to resist in the same level. So there will not be any further increase in the resistance, but the displacement, I mean, the softening happens in the weakest link. Here in this subsystem, which is the one, the green color is the weakest one. So until the peak point is reached, we keep on adding the displacements to obtain the rising limb. And beyond that, the exact same pattern of the falling limb have to be followed. Here we should not add the displacement of the other component pairs. There is no point, because the plastic hinge is happening only in the weakest one, that is in the subsystem 9 to 13. Here it is getting separated. The top portion, that is getting separated. That is the scenario. Because in that level, 9 to 13, all these component pairs are sliding critical, and also that is the weakest one. So in that building, the top portion is, in that wall, the top portion is getting separated and moving away. That is above the lintel. See this discretized wall 1, no? This entire wall above the spandrel above, 9 to 10, 9 to 13, they get separated in the sliding mode. So that is the type of behavior that we are assessing from the development of by developing this capacity. While we do that, we are obtaining this pattern. Okay. So now we have got the wall 1's capacity curve, which is that the violet one. Along the y direction, we saw there were 3 walls, wall 1, wall 2, wall 3. In the same way, we can get the capacity curves of wall 2 and wall 3 also. The same procedure what we adopted. And then to obtain the capacity curve of a building, again we'll have to go back to the resisting force in parallel action scheme. Because wall 1, wall 2, wall 3 are parallel springs. They are a composite springs by themselves. Wall 1 is a composite spring by itself. Wall 2 is composite spring by itself. And wall 3 is a composite spring by itself. And this fixture spring, wall 1, wall 2, wall 3 are resisting force in parallel action. For this also, we will have to add the resistance and follow the same principle what we adopted for the case of spandrel or sill. Now, you see there are 3 lines. That is for wall 1, blue color, wall 2, red color, brown color, and wall 3, green color. And for the building, they resist in parallel action, force in parallel action, and so the resistance are added at each and every level. And total capacity curve is obtained. So what we are seeing, it keeps on increasing, and then we are realizing that the red one starts getting into the nonlinear range, and then the next stage is attained in the same red color one, that is wall 2, something like that, for each and every point of direction changing. You have to obtain the ordinate and then connect them to get the capacity curve of the building. So this is the way how we get the capacity curve of one building along one principal direction. So this procedure we adopt to get the capacity curve of buildings. Okay. To study the applicability of these damage grades, especially to study what is the lift needs for typical low-rise brick masonry building in India. What we have done is we have considered some 35 typical low-rise buildings of different plans, something like this. Okay, and then we have developed the capacity curves for each of these 35 buildings. It is along for each and every building there will be 2 principal directions and 2 capacity curves along x direction and y direction, isn't it? So for the 35 buildings, what we are considering, we will have 70 capacity curves. For a same building along x direction and along y directions, x and y direction, we'll have a distinct, totally different capacity curve. Resistance also will be different, and the displacement, ductility levels are also different. How to classify them? How to understand them? How to bring some kind of a judgment? And define the measure and then grade them. That is the point, isn't it? As I told you in FEMA, we had this drift ratio, fixed value of drift ratio. And then they went into the deformation controlled drift ratio limits. Drift ratio, fixed values, and deformation control, drift ratio limits. Okay. Now what we are trying to say is that now we have had 35 buildings. For each and every building, we have set of parameters that probably may influence the behavior, right? So what are all those behaviors? By and large, engineers will be looking at the vertical aspect ratio, whether the building in overall sense is a slender building or a squat building, so that the overall bending behavior will be significant or overall shear failure will be significant. That will be defined by the aspect ratio of the building, and then plan area, structural plan density, that is flow resisting area divided by floor area. Okay, I think I'm nearing 1 hour. Okay, I'll rush up. Okay, so resisting area to the floor area, that is called structural plan density, and perforation area ratio, that is overall area of the wall, area of the opening divided by overall area of the wall. All these are having some kind of an influence in the overall resistance. But depending upon the geometry, variation in the geometry, their locations of the piers, will get a lot of scatter. In this 35 buildings, what we have considered, these are all the geometrical parameters that we have considered. See here in the right column, we have seen the coefficient of variation in their statistical values. All these are showing significant disbursement. That means that the buildings what we are considered are not very narrowed down class. It is one type of building, but the scatter indicates that it is a overall representative, a good representative of typical class, typical structural brick masonry buildings, low-rise actual brick masonry buildings with rigid height. So this COV value is showing us that this is a fairly representative sample. And now the main part. I told you, we have considered 35 buildings. And for each and every building, there will be 2 principal directions, and so we have 2 capacity curves. These are the capacity curves along 2 principal directions of those identified 35 buildings. Now you can see the capacity curves. All of them are single-story building. All of them are having similar sizes and geometries, but their positions of opening, sizes of opening, number of rooms, these are all only different. But see, the capacity curve is showing a large variation, right from 20 kilonewton to 160 kilonewton, and from say 0.02 mm to 0.2 mm. Such a large scatter, both in capacity ordinate and also in the drift ratio ordinate. And importantly, the drift ratios are also significantly varying. Ductility is also. Ductility, suppose if we have some kind of a similarity in ductility, isn't it? The AAC method will be applicable, will be reasonable, because the displacement characteristics is displacement. I mean, the measure is in terms of ductility. But here you can see small the buildings with smaller ductility and also buildings with larger ductility. And so, see, the FEMA 356 giving fixed limit. Supposing if you are considering a point of 0.025 drift ratio. Okay. Now, if you draw a vertical line, each and every capacity curve will show us that particular building along that particular direction is in different level of non-linearity or linearity, whatever it is. No? Initially, it will be linearity, and then beyond that, it will be non-linearity. They may be in different levels of different levels of the non-linearity range. It might have still in the elastic form, elastic level, or it would have reached the near peak, or it might have been in the softening part or in the collapse part. Even at that low levels, you have samples of different structural performance level. So that's how they also stopped using fixed values, but they came out with the drift ratio, I mean deformation control, the ductility ratio limits. What we are observing is that the ductility ratio themselves are having large scatter. So to define a damage grade, the ductility ratio also cannot be used. Or ductility or the measure which is controlled by the that's what they call the deformation control ductility ratio limit. That also is not possible. And so we come out with the structural performance characteristics based damage gradation. So what it means that damage grade 1, what it is says, the earlier of initiation of non-linearity in any of the component pairs or attainment of 33% of base shear in the rising link. What is that? Either some part of the building or getting into the non-linearity. I told you, they progressively get from the development of capacity curve, we would have realized that the non-linearity is happening progressively, component by component, isn't it? So what is which component is attaining first non-linearity? That is damage grade 1. If supposing if the level of it is it happens just before attainment of peak or very close to peak, will it be acceptable? No, right? So what we are saying that in that case, when they are not so close, and when they are so close, initiation of non-linearity and attainment of peak base shear happening at a closer spacing, what we'll have to do is you bring the damage grade to the 1/3 of the attainment of peak base shear. So in a capacity curve, we will get the damage grade 1 marked down to, and then attainment of peak base shear. Okay, and then in the falling limb also, we can have a cutoff of say 60%. So beyond that, it can be considered as a collapse. So what is that drift ratio? That becomes the damage grade for damage grade 3. So we have damage grade 1, which is the drift ratio corresponding to the initiation of non-linearity or attainment of 33% of the peak base shear. and then damage grade 2, which is again the drift ratio corresponding to the attainment of peak base shear, and then drift ratio corresponding to the attainment of 60% in the falling recession. Now one can argue, sir, this is also a subjective description, isn't it? Because it merely tells, it doesn't give fixed value, it doesn't give any other thing, it gives you some definition, some descriptive definition. It is a descriptive measure, agreed. But the difference between the other subjective measure, what we are talking, smaller crack, fine crack, fair crack in the buildings, wide crack in the buildings, can they be marked onto the capacity curve of the building? No. But this description can be mapped on the capacity curve, so that when you are performing the analysis, get the capacity curve and get the drift ratios corresponding to these three damage grades separately. For each and every building, now we will have fixed values. It's not for the class of the buildings will have fixed values, which is not relevant, but we can have a fixed value for each and every building along the respective principal direction. But this damage gradation gives the scope for defining in terms of character, structural performance character. So this is the concept that we have brought in for, and then the all other things, or further details on how we have given justification, all that. Okay, as we are also running out of time, I have crossed 5 minutes beyond the time, beyond the given limit. So I will stop here. But this is available in a paper, which we can refer to, a detailed description, a detailed method of assessing why and what, how to corroborate, all that we have carried out to give the justification and end up in this damage gradation, structural performance based damage gradation. So, and this is the topic I wanted to cover. Now you can ask any question if you have.
Thank you. Thank you so much, Professor Balasubramanian sir. Thank you for giving a complete overview on the damage gradation for masonry buildings in particular. So, Kavya, it's over to you.
Thank you, sir, for that insightful and inspiring session. Now we'll take the questions from the participant.
Okay. Sir, you can unshare your screen, no problem.
If they ask again,
okay, fine.
So we have to go to the respective slide and show.
Okay. So I'll read out few of the questions. So the first question is how we can decide by the capacity curve and the damage gradation whether the structure needs retrofitting or not.
So what we can do is we can get the capacity curve. From that, what we can obtain is the drift ratios for each and for that particular building. See, giving fixed ratios for the entire class of buildings is not correct. But for the respective building, we can get the drift ratios corresponding to damage grade 1, 2, and 3. Supposing if you consider this particular case. Okay, sorry. Okay, example problem. No, we will go to that example problem.
I think it is given in that Word file.
Yeah. Now please refer to this violet color one. This is the capacity curve along y direction of that building. Now what happens is this point, that is around the 42 kilonewton, no? 42, 43 kilonewton, that is the damage grade 2. Okay. And first point, somewhere around 32 or something it is coming. So by definition, it is very close to the attainment of peak base shear, and so 1/3 of the damage grade 2 will become the damage grade 1. So somewhere around 16, sorry, 13 or so, isn't it? Here. So the drift ratio limit will be around 0.1, 0.42, 0.13 and 0.42, and then falling, in the falling limb you have the 60%, 42 somewhere around here, somewhere around 0.6 drift ratio. So we'll have this 0.13, 0.42 and 0.6 as the drift ratio limit for this particular building along this particular direction. Now we can carry out incremental dynamic analysis or pushover analysis, and using this ATC40 method, we can superimpose the capacity curve and get the performance for that particular spectrum. We'll get the drift ratio, that maximum drift ratio on that spectrum, right, in areas format. So that value we will have to compare with these values, DG1, DG2, DG3, and say which is the damage get that building in that tube for that particular target spectrum. Similarly, if you perform incremental dynamic analysis also, in each and every intensity we'll carry out time history analysis. We'll get the maximum time history, maximum displacement, right? That peak point displacement we will have to get and compare with the DG1, DG2, DG3 and say which that building will be in. At the end of this shaking, the building will be reaching that maximum level. We can come out, right? So that's how either way we can go ahead. In earlier we had fixed values. Now for the entire class of building, for here with this, for the respective building, we will have the fixed values and then we'll compare with the performance points.
So from the demand curve and the capacity curve, how an user will get to know that whether the structure needs retrofitting or not, just by seeing the that was the main
question. Knowing the damage grade.
Okay.
At the end of either ATC method or incremental dynamic analysis method, we will be in a position to say what is the damage level it would be attaining theoretically. If that performance level is acceptable, we can take a call. There is no need for retrofitting.
Okay. So based on the acceptance criteria, one has to.
Then that is the next stage.
Okay.
Qualify. But to identify in which damage state or to identify in which level of the non-linearity it would have probably gone into.
Right.
We need this.
Okay. Thank you, sir. The next question is related to the openings. What should be the maximum percentage area of openings with reference to the wall surface in order to achieve the satisfactory structural performance? So is there any specific criteria or codal guideline is available for this?
While defining that, rightly speaking, zero value is the from structural performance level. Zero is the desirable one.
You do not want any openings.
Yeah, right. This is required from multiple aspects.
Multiple aspects.
Functional performance of entry, functional performance of daylighting, functional performance of ventilation, All that comes into picture, and then we have to take a call. There are limits in IS 13828.
1382.
Yeah, 13828. A schematic diagram and the limits of openings and
Door and windows.
these
Yeah.
things are there
Sizes and give.
from ventilation, daylighting point of view. Though it is also a broad one, because a building located in Guwahati will be different from a building located in Hyderabad, will be different from a building located in Kutch.
Right. True.
Isn't it? But in overall, they have given some practical range of minimum widths and maximum widths. All that is there.
Okay.
But what we can do is we can alter here and there, but to play with the optimization or trying to bring these capacity curves in a better way, we'll have to either depend on improving and some kind of a ductility tooth reinforcement or something else. We cannot play with the geometry like the case of the reinforced concrete buildings or steel buildings, where instead of, suppose if one want to change the dimension from 300 mm square column to, they can change to 350 mm square column, still can. But here the geometry is defined by multiple factors.
Okay.
So we'll have to depend on other means of strengthening inherently.
Okay. So the next question is related to the pushover results. Suppose you are whatever curves you have shown, right? You are analyzing a pushover results. If the capacity curve shows a early drop in strength, right? So what structural deficiency might be present just by seeing the pattern or the trend of a pushover curve can be identified? Is it practically possible?
Possible, sir. The thing is, when we are assembling, we will be knowing how each and every component are behaving, and just from the overall capacity curve, we will not be able to say it concrete. But when we are assembling, we will be seeing the progress.
Yes.
While assembling, we will be seeing the progress. That's where we will come to know which part of the spandrel or the pier portion or the sill portion is weak, or in that which component is giving problem to that particular zone. Suppose in a pier portion, a small slender masonry portion adjacent to the corner of a building next to doors, that pier will be very, very weak.
Yeah.
What will one from assembling? What will you can see that particular part will bring down the entire capacity of it. So what we'll have to do is, when we are devising the bringing out the structural retrofitting schema, which is the one which is so sensitively bringing down, if we can address there, the overall performance will increase. Okay. Isn't it?
Right.
If we can that we can identify while assembling. At component level, we'll get the capacity curve, and then we'll get the system level, and then from the to the wall level, and then to the building level. Right. So from this progress, we will be able to get the weakest one in the respective wall, and that if we can address, improve that particular thing, we can significantly vary the capacity curve. Strategically addressing. This also possible. That's where this importance of story shear modeling comes at the macro level, because where is the weakness that we can identify significantly, and then we will focus more on that in retrofitting.
Right. Okay. So the next point is, what does the area under the capacity curve represent, especially in terms of energy dissipation during an earthquake?
It is same concept, sir. Like in the case of concrete or steel buildings, it is the resilience, energy absorption during the shaking. Okay. But though in these figures, they are looking little wider in sense. But if you compare the case of steel buildings or concrete buildings, reinforced concrete buildings, with lot of ductileness in the air, in the air, in their hinges, the resilience will be significantly higher, but
Higher.
that will not be there in the case of masonry. Though we are having in the case of sliding shear failure or in the rocking failure, the actually allowable displacements can be much larger compared to the attainment of the beam.
Mm.
Because now you see, this is a slender pier. Okay. It initially what happens? It separates, the heel separates, and the toe gets crushed.
Mm.
Isn't it? So it attains the peak, but it will not lose the integrity till
Mm.
the center of gravity falls beyond the corner.
Corner, yes.
That displacement will be significantly large.
Significant.
But our analysis, what will be restricting is 2.5 or 3 maximum. We
Right.
restrict that, and so we'll be seeing such things.
Okay.
So,
So,
and no, I mean, we are not confident enough to take the higher ductility values also because
exactly.
of the uncertainty associated with many other aspects.
So my follow-up point was related to the ductility only with respect to that question. Suppose if a structure has a very short yield point, if the yield comes out to be very, very small, then what does it tell about the ductility?
What it means that the structure in overall behaves as a single box.
Single box.
See, what we have to see is, unlike the reinforced concrete buildings and steel buildings, here we will not go in terms of ductility. Here resistance is important. As long as the building is in integrity, I mean building is intact, the resistance keeps on increasing. It is the resistance that is going to govern, especially in this case, because these buildings inherently have higher rigidities.
Hmm.
They behave, I mean, in a sense, they will be very sensitive to the acceleration, unlike the reinforced concrete or
Steel building.
steel buildings of higher stories,
Right.
high story reinforced concrete buildings or steel buildings. They will have their fundamental period will be very significant when compared to the fundamental period of masonry buildings. These will be like a solid box.
Right.
Once the separation happens, it is going to fail.
Okay. Sir, there are few more questions we'll take up and it is related to the performance-based seismic design, which you have initially highlighted. So
Yes.
the first question is, you talked about some performance objectives, right? Or performance levels like immediate occupancy, life safety, or collapse prevention. So the question is, what is the physical interpretation of these different performance levels?
See, the thing is, the concept of that life safety,
Immediate occupancy,
life
life
safety, and
safety.
collapse prevention is that from the capacity curves, they were trying to get in which nonlinearity they were.
Right.
Yeah. That's the basic thing. So what they thought, some 3 limit values they gave. And unlike the other older gradations, what they were thinking is, we'll give whether it is in the elastic regime, or it attained peak, or it is in the softening thing.
Right.
That is the basic thing. With that idea only they brought. But the problem is, for all other buildings, the scatter limits were perhaps could have been smaller, and so there can be a small defining bound. But looking at the dispersion of, in the case of masonry, with even with the smaller changes in the geometries of the typical buildings, you will see large variation in the capacity curve. So getting them bounds and getting a bound and then giving a conservative limit and all, it is not possible.
Okay,
That
sir.
is why they themselves have stopped and they started giving from displaced deformation control limits. What they started doing, delta 1 by delta 2, that number and all they started defining,
Right.
isn't it?
Yeah. So,
But there also problem again comes is ductility is also not uniform. They are also having large scatter.
right.
So giving them a measure within that also is not reasonable. So that is why we go back to the old school, which is the plastic regime that we are looking at. To define that plastic regime, better we get into a subjective description, but that can be marked onto the capacity.
Marked on the capacity. Okay. So,
So get back to the
got it, sir. Got it. So, since we are talking about this immediate occupancy, life safety, and collapse prevention, so like in FEMA 356 or ASC 41 2023 also, there was few acceptance criterias were given based on the actions, in plane actions, and for unreinforced wall and for reinforced masonry wall. Why all these acceptance criteria are reported only in terms of displacements? Why not in terms of force? Is there any specific
controlled? Because they
displacement control.
They dropped the fixed ones.
Right.
They started giving in terms of, so that concept they did it in the case of that was suitable for reinforced concrete buildings and steel buildings where they have because that ASC 4113 or the FEMA 356 they are not restricted to masonry buildings alone.
Yeah.
They are talking about different.
It's given for different type of materials.
In the similar trends they have used, but for masonry, that treatment itself is unrealistic because of its inherent behavior. One, it is sensitive to acceleration because of the resistance. Seismic resistance is of important, where the seismic resilience is important. The perspective with which this has to be looked at is entirely different.
So is there any possibility of inter-story drift limits for different performance levels? Is it possible?
That's what we are saying. But for class, we are not giving. What we are saying is we are giving this method of fixing values for each and every building. We have to get those values. After getting the capacity curve, we have to get the limit for that particular building along that particular direction. Because naturally we need some objective measure.
Right.
For our analysis and for comparison purpose, for screening and other things, we need the values. But what is the value? What are all the limits? That is not fixed one or deformation controlled one, but a force control characteristics one.
Okay, sir. We'll take last 2-3 questions and then we'll wrap it up. So the question is, in the real seismic events, how reliable the laboratory obtained drift limits? Suppose we test a wall and we basically find out an in-plane drift limit or for an out-of-plane drift limit in predicting the actual building damage.
That depends upon the rigorousness of the model.
Exactly.
All that we are performing analysis with some kind of a approximation. So how far we are approximating, that far we will be ending up the realist.
Right.
We always
whether we have chosen
the thing is, sir, in this, so for at least for a monotonically increasing force, some kind of this thing confidently we can talk about it. But in the case of
Cyclic.
dynamics,
Hmm.
because of the idea curve, see, it is slowly increasing. We are slowly increasing the intensity. But idea curves, do they fall in the same pattern? No. They fluctuate. Why?
They fluctuate.
That is the nature of vibration. That is the nature of shaking, isn't it? Monotonically means if you increase the displacement, see, force naturally displacement will increase. But in the case of dynamics analysis, idea will not be happening. It is not monotonically. It is fluctuating. Similarly, small approximations here and there will also be reflected in the actual analysis, estimate and the realizing what we are realizing.
I think also the boundary conditions when we do any experiments, how realistically we are trying to simulate, that also plays a crucial role.
That is where we were talking about that in the improved story shear modeling chapter I was talking about. No, in this conventional story shear modeling, we had only two options: either as a cantilever or a fixed twist boundary condition for the component piers. So we brought in that partial fixity conditions depending upon continuity above.
Continuity, yeah. Got it, sir. There is a question like, how do factors like masonry properties like mortar strength, brick strength, and the quality control, especially in terms of workmanship variability, influence the transition between moderate and severe damage grades? Because when you talked about the damage grades, there are different grades, right? Grade 1 to grade 5.
We have performed a sensitivity analysis with respect to this, the same 35 buildings. We have carried out incremental dynamic analysis for these buildings, for one building, with variation in COV.
Okay.
And then we performed a multi-record incremental dynamic analysis, and also we used single record incremental dynamic analysis for different earthquakes.
Okay.
So you consider 12 earthquakes. Okay, we got multi-record incremental dynamic analysis fragility curve, and also we got fragility curves corresponding to each and every earthquake.
Okay. And also the different parametric studies have also been performed by varying the
with different COVs.
COVs, okay.
What we have identified is that the variation in COV is not that much significant when comparing to the earthquake parameters. Earthquake parameters are much more significant. Here, the geometry of the building is significant. And then earthquake characteristics is significant. The COV scatter in the mechanical properties is not so sensitive.
Okay, sir. There is a question on what inspection parameter should be prioritized immediately after an earthquake for masonry structures. So I think it is related. The question is mostly related to the post-earthquake assessment kind of a thing.
For this, we will have to go to that damage score by Professor or CBRA director. It is a comprehensive score.
Professor Pradeep.
Professor Ramacharla Pradeep Kumar. The damage score system, I am always having a good regard at. Because you do not have to perform analysis. You give certain score weightages for different observations, and then you end up giving some estimate for. But that is not purely structural. But it is a it's a composite in overall sense.
Okay.
So Professor Ramacharla Pradeep Kumar, this damage gradation score, that is for the post-earthquake damage surveys.
I think in the new version of IS 13935, maybe part 1 or part 2, they have gone
it has to be
incorporated, I think.
But this damage gradation is for performance-based design. where we look at the building in particular, their damage score is for the entire community or
Yes,
locality,
yes.
different class of building. That
Right.
is for from administration perspective
Yes.
or decision.
It is in the broader aspect.
Yes.
It is in the broader
This
aspect.
is building specific.
Building specific. And I really like the concept, because usually when we talk about the damage gradation, most of the gradations are given qualitatively. But the concept which you have shown, where you have quantified, like you have said 33 kilonewton value, it is corresponding to a specific grade, 50 kilonewton representative to a specific grade, and then you have bifurcated in terms of different classification, right? It's really helpful in understanding in which category the damage is likely to occur with respect to a particular capacity curve. And in terms of generalized thing, one can normalize all these parameters and can check whether your building needs that particular structural retrofitting if it goes beyond a specific damage. Otherwise, with a small repairing work also, it could be undergone.
We'll have to do again that. What we'll have to do is look at the weakest one.
Weakest one.
Improve story the capacity of that one.
Yes.
Get the revised capacity curve, perform analysis, and see whether the target is met with.
Right.
That's all.
Okay.
It is iterative procedure.
So the last question of the day, because in our discussion and also in the presentation, we have used, there are two terms constantly. One is pier, another is spandrel, with reference to a masonry wall. Could you please clarify for the audience what exactly the pier and spandrel is all about?
Okay. Yeah. All of our people are not.
Because many of these students are not aware of these masonry specific terminologies.
I missed to.
No problem.
I'll show you something.
No, maybe with that in your slide as well, where you have shown a wall where there was an opening. Yeah.
So, dear friends, you are able to see this. Anybody else?
I think. No, sir. Everyone is able to see.
So I just wanted to confirmation from others.
Yeah, sure. Yeah, anyone can respond, please, whether you are able to see the slide or not.
Yes, sir, we can.
Yeah. Thank you.
Here this is a simplified version of a simplified sketch showing the parts of the structural brick masonry buildings. Like we all have head, body, forearm, arm, legs and all, isn't it? This is the organs of the structural masonry buildings. So what you can see is, we'll go from the bottom. So below the window level, see the bottom of the window is called the sill level, isn't it? Below the sill level, the portion of masonry is there, isn't it? This is called sill masonry. And then above lintel, we are having some forehead kind of a thing, no? Isn't it? So that is called the spandrel masonry, and the portion in between, by and large, referred as pier. You would have noticed I was using cautiously one term called component pier.
Component pier, yeah.
Component pier. What I mean is that this component pier. What I mean is that here we are having a spandrel, which is not one element. That is also subdivided into multiple piers of multiple springs. That is why in those places I used the word component pier. Component pier means here you have 1, 2, 3, 4, 5 component piers in this spandrel.
Yes.
Something like. So this is how we use this term: spandrel masonry, pier masonry, and sill masonry. And the new term, that component pier, I was talking about. capacity. For each and every component here, we can get the capacity curve, and while assembling, we will be able to get the all this based on load sharing path only. Spring, nonlinear spring, everything we are studying. Same thing, but this we are simply adopting the load sharing path. We
Okay.
use that. That's
Okay, sir. Thank you so much. I think we have you have clarified the questions of all the participants. So thank you once again for joining for this specific event. Now it's over to Kavya. Kavya.
Thank you, sir. I believe the queries from all participants have been addressed. Now, I would like to invite Mr. Vikas to deliver the vote of thanks.
Sir, you can unshare the screen for the time. Yeah.
Greetings to all. I am Vikas Medari, pursuing MTech at Earthquake Engineering Research Center. It's my honor and privilege to deliver vote of thanks on behalf of entire executive committee of IX30 IIIT Hyderabad student chapter. First and foremost, I extend our deepest gratitude to our esteemed guest speaker, Dr. R Balasubramanian, for his insightful presentation and enlightening session on seismic damage gradation for structural brick masonry buildings. Today's webinar has highlighted the importance of seismic safety in brick masonry buildings, classification of different grades of damage under earthquake loading, and comparison of seismic damage scales. So, behavior assessment of capacity curve with improved story shear modeling with examples, and damage gradation based on structural performance characteristics. Moving on, I would also like to express our heartfelt gratitude to our faculty advisor, Dr. Praveen, for his continuous guidance and valuable suggestions throughout the planning and execution of this event. A special mention goes to IT team for ensuring seamless technical support and to the designing team for the creative inputs and logical assistance. I thank our program coordinator, Dr. Sunita Palisari, for her continuous encouragement. I also want to express my appreciation to all the participants for their active involvement and thoughtful questions, which enhanced this discussion and made this webinar a collaborative learning experience. Lastly, I would acknowledge the hard work and dedication of entire team whose collective effort has made this event a success. In conclusion, I extend my heartfelt thanks to each one of your participation and engagement. We are extremely grateful and looking forward for your continuous support in our future initiatives. And thank you.
Thank you. Thank you,
Thank you,
Vikas.
sir.
Thank you so much,
thank you,
sir.
Professor. Thank you,
Thank you.
for giving me the opportunity. Hope we would all got something to take away.
Absolutely,
For
sir.
everybody, I mean,
Yes.
all the students. And
So we will gonna upload this specific session video to the official YouTube channel of
fine, Professor.
IIIT, and I will also share a copy of that with you.
Fine,
Yeah,
Professor.
link. So
Thank
okay.
you.
Thank you. Thank you so much. Thank you to all the participants for joining the event. So here we conclude. So that's it. Thank you so much. Bye.
Okay.
Okay, sir. Mahesh, kindly stop the recording.